I think the key word here is uncertain. There's an uncertain environment. And in the case where you have a more certain environment, some ways of working fits very well. And in the case of uncertain environment, other ways of working fits better. So it's not that one method or tool or whatever is wrong. It's just that you need to apply the right tool or method in the right place, in the right situation, in the right environment. So just to sort of give an example, over 100 years ago, no one knew how to fly. It sounds ridiculous now, I guess, but we didn't know what it took to get airborne. They did what any sensible person would do. They gave a lot of money to one person that they thought were really, really smart, and that person designed the perfect theoretical solution based on the current knowledge they had and built one flying machine that never flew. And that's maybe, most people have maybe not heard about Samuel Langley, because he was not the one who invented flight, even though he tried his best. Then we have these fellows. Maybe you've seen this picture before. Actually, the first flight. And they had a bike repair shop, these two brothers. Basically no money, but a lot of interest, a lot of grit in trying things out. And they kept doing this for years. And then in sort of winter time, they repaired bikes and thought about things and tried about small models and things. And in the summer, they went to this dune and tried to fly machines. And they failed one summer, and they went back the next summer, and so on and so on and so on. And in the end, they made it. So we're now looking at two sort of approaches to this. Best current knowledge, a lot of funding, build one thing, and it turns out we had too little information. It was too uncertain, the situation. And in the other situation, they acted on their right. They didn't even know what it took. But they actually ordered all the books that were available about flight and read it all and concluded that it's not in here. We need to experiment. So that's what they did. And they started with trying to figure out different aspects of flight one by one. Instead of saying, we're going to build one machine that's going to fly the first time we try it, they try to figure out, how do we get lift? How do we design wings? What's needed to get lift? And they even started to design like wind tunnels and tools and infrastructure that they needed to do this discovering, creating new knowledge. That's the thing here. Uncertain situation, create new knowledge. Learning. Yes?
I went to the Air and Space Museum on Sunday.
Oh, okay, yeah.
I read all about this.
Okay, yeah.
So I went to the where they showed everything. And they even, there were coefficient for lift that they used.
Yep.
And it was wrong.
It was wrong, yeah.
And they found out this one,
yes,
which is very accurate what we use today.
Yeah.
And that was in the 1900s.
And that was also one of the reasons why Langley failed, because he used conventional wisdom, the wrong constant in a way.
And that's why they did fly 1900, and then in 1901 they failed.
Yep.
Because they used it wrong.
Yes.
And then they needed to realize what's the right one.
Yep. So experiment, and get new knowledge, and so on. And then when they had lift, they could go on to control. How do we control a flying object? And then they could add more power to it, propulsion, right, and get refund. And there's no reason to add other complexities. If you don't know how to lift something, you don't need control or propulsion yet. So, depending on your situation, what do you need to learn, actually to experiment and find knowledge, and when is it a clear enough situation where we know how to do this, there's an engineering best practice, let's just do it. And those two are different. And it's really, really important to keep track of where we are, what kind of environment we're in. So that's why we talk about fast learning cycles. Because maybe a situation is that it's geared to a clear situation where it's clear what to do. We'll have a lot of best practices and things to do, and an optimized process to do exactly that. But when we're optimizing for learning, we probably need to do something else. And we need to discover what that is in our case, in our field. And we need to have ways of working together that is helping us to do this. That's why we talk about small batch sizes and doing smaller increments and so on. If you have uncertainty, like inside this room, I could probably, it's safe enough to just close my eyes and just go in a direction. It's probably okay. If I'm on a hill and there's a steep down, I probably go very small step. Because it's very uncertain. So it depends, like how much do you want to risk? You want to risk 2 weeks of work, 1 month of work, 1 year of work in one direction? How certain are you that you're heading in the right direction? Those things will count when it comes to how to approach a problem. Also, when you are dealing with hardware and larger solutions, usually, I guess a simple hardware thing, this pen or something, could be described as simple. But the computer or truck or whatever kind of things that you're building, it's probably going to be huge and a lot of things that need to fit together. Well, how do you know that you're at some point of learning? Well, there are different ways of doing it, but one certain way of doing it is trying to put it all together and see if it works. Even though you did wind tunnel testing with small, like 3 models of a plane and so on, at some point you actually want to integrate that and see if it actually flies. And those integration points might be smaller and larger depending on how costly it is to get to an integration point. But also you can optimize your process to be able to get to integration points more often, more cheaply. Because again, you want to get to learning faster. So let's just sort of look at a little bit of an example. What you see here is a few slides from the training, by the way. So you see there's a lot of bullet points and a lot of text that might not be exactly relevant today. But just to sort of see that if you have a vehicle and that vehicle should be autonomous, you should probably need a camera or several cameras to look outside and see what's happening in the world. Let you zoom in on that and see what kind of interaction does that camera have with its surrounding. Well, it's mounted to the chassis of the vehicle. It also sends the image, the video, to the navigation system so that it can make decisions on how to act on that video. Okay? This is very important to be able to break the larger solution down into pieces that we can work with more independently. So, for instance, the camera itself might have very clear interfaces towards you. You're going to just use HDMI, just send the signal to the navigation system. And we have a deal with the chassis people around how it's going to be mounted, what kind of force, what kind of temperature, what kind of things that we assume that this interface towards them is going to be. So within these things, we can work more independently now, as long as we keep the interface. Right? This is hopefully known and things that you already use in modularity and so on. But it also allows us to work more independently and have faster iterations within one of these modules or components, where there might even be several technologies or several engineering fields working together to get a better camera version out there. And what we're saying here is that we probably, because there are so many unknowns, and things are going to move, technology is going to move, market demand's going to move, suddenly they say from navigation, there's probably some sort of machine learning or AI, you know. Like, this camera isn't working, we need better resolution of the images. Okay, so now we need to change that. How do we change that? Okay, maybe you need to change some physical hardware, or can we do something smarter with the firmware? Can we update the firmware? Okay, how can we make sure that we're designing and building options into the hardware? Maybe a little bit more expensive, but now maybe we can program chips, for instance, have those types of devices parts of the solution that will allow us to change things later and not set things in stone too early. Which you want to do in a clear situation, because then you just want to find the most cheap part from the best supplier, just put it there, it's going to be there forever. But in a very uncertain situation, or at least uncertain enough, it might be worth the extra cost of getting flexibility. And if you have a system today that's very geared toward more certain, we've done this for 30, 50 years. I just returned from Linköping and Saab today, and they were like, the last time we built something new was actually 1982. That's when JAS Gripen was ordered by the state. That's when they started with something really new the last time. And they said, like, we don't have anyone left. Like, everyone is not dead maybe, but at least they left the company, right? We don't know how to do new stuff. We only know how to optimize Gripen, and they've done it a really good job. Like the last version, Gripen E is great, but it's just updates within the exact same form factor, for instance. So it depends. Like, your organizations might be more or less geared toward being able to think in this way and take opportunity of these types of flexibility that might now be needed for your product, depending on where you're heading and where your markets are. And lastly, sort of just going to mention that there's probably going to be some sort of release pipeline where you're probably going to start somewhere more in modeling, trying things out in prototypes, making sure that those prototypes are compatible with the way that we want to manufacture things. So design for manufacturability and so on. But also making sure, can we collect data from the real environment where our stuff are in, so that we can learn. How do we need to change the product? So there are a lot of feedback loops, and also cheaper in the beginning to change things, but also having infrastructure enough to be able to do prototypes. To maybe do some sort of manufacturing in small scale to validate that that's possible, or at least model that part out. And that's going to be different for different scenarios. All right, so we basically done a little bit of dipping the toe into design for change here. We're probably also going to need to talk about how do we specify and deal with specifications more incrementally, so not when we have to specify everything up front and then it's going to be delivered. The first JAS Gripen fighter jet was delivered in 1996. was ordered in 1982. And it was conceived, sort of thought about how we're going to do it in the 70s. And that, I totally understand the lead time there, but there was a lot of specifications being done up front. And a lot of technology development that happened during the specification phase and so on. So how do we move a bit faster forward, but still having the right documentation being compliant and so on? And how do we plan this? We're planning what this engineer is going to do this the Tuesday in 3 years in the plan. Like, that's probably not the right sort of fidelity of planning compared to, but also roughly what we're going to do in 3 years. Well, roughly this area. We're going to do propulsion because we're going to do lift now and so on. And how do we get this frequent integration and the infrastructure needed to do that while being compliant? We can't dodge those things, right? Quality, or lower quality is not an option. But can we work smarter with that? And the same way, can we work smarter with our key suppliers? And people who've been working lean, there's no news here, like partnerships, being really good with how you deal with your and interact with your suppliers.